So next we're going to look at graphing decay with the transformations. I really hope that right now, if you were to think about this and actually take a moment to do that, pause for just a moment and think, how is this going to be different than what we did in graphing growth? I hope that your answer is that it's just flipped that direction. Because if you go back to that first video, there's that idea of 2 to the x power and 1/2 to the x power are actually just symmetric around that y-axis. So, and that is true, that what we're going to expect to see here is just a graph that's on the other side. The dots go up here. They also get closer to the asymptote on that side. Now, my procedure for doing this is all pretty much the same thing. The constant that we have at the end is the -5. So that's going to shift the horizontal asymptote down to -5. We do have a +3 here in the exponent, so that's going to shift everything to the left at a -3, and I went ahead and drew those lines. I'm going to treat this as if it were my origin. And now I'm going to start to build the table, except I happen to have a base that's 1/2. So you still got your basics here. Anything to the 0 power is 1. If you raise this to the first power, you get back your base, which is going to be at 1/2. Then we choose a couple extras. If you do 2, this is going to be 1/2 squared, which is going to give you 1/4. 1/2 times 1/2 is 1/4. A half of a half is 1/4. Okay, so this is going to create, if you go in this order and increase the numbers, you're actually going to get your fractions. So if we go the other way, if we use -1, -1/2 to the -1 power, let me write that one down so you can see it. That literally just means take a reciprocal, so you get a 2. Okay, and then if I do -2, that literally means take a reciprocal of it and square it. So the reciprocal is going to give you 2, and when you square 2, you get 4. Now, I don't have my table lined up in order like where these are completely increasing, but if you rearrange it, you're going to see that symmetry that we had in my review video. Okay, so then now graphing, I go over to my pretend origin, and I start moving things. There's no A value here, so we don't got to adjust. We can literally just use the numbers that we've got. So that one's going to be up 1 unit. We're going to go over 1 unit, but only up 1/2. We're going to go over 2 units and just up 1/4, and then it's settling off at that asymptote. The other direction, when you go -1, it's up 2. -2 is going to take you up 4 right there. So your graph is just backwards from if you had a 2 down here. Domain. At this point, it should be getting a little bit boring answering the domain part of this. It's all real numbers. Your range, we are bounded at -5, open parentheses, and we're going to go up to infinity. Example number 2 is also going to be a decay function. Of course, it is part of the notes. I just presented it a little bit different as a base. I called it 0.25, but that's the same thing as 1/4. And I think that as you start to come up with your numbers, it'll probably be better to keep it in a fractional form, because negative numbers for x's are just going to flip that over. And it might look a little bit difficult to try and take a reciprocal of a decimal. So I'm going to change it up as I think of it later. Okay, shifting, we don't have any constants, so our asymptote's going to stay here at 0. We do have a shift to the left 1 unit, so I drew a line there, and this will be my pretend origin. So I'm going to go over here and start making a table of values. If I had 1/4 raised to the powers, here's your basics. Okay, if I do something like 2, it's going to square that, which gives me hardly anything there, 1/16. But if I go in the other direction, I start getting my reciprocals out of this. So I get those numbers. In addition, though, we got that 4 that's in the front. So that 4 is going to magnify all of these numbers by 4. So when we actually graph, you want to be thinking that one's a 4. 1/4 times 4 is going to give you a 1. 1/16 times 4 is going to give you 1/4. Yeah. All right, and then here it's going to get a little bit crazy, because 4 times 4 is 16. 16 times 4 is 64. You're not going to get anything out of that. Okay, so now graphing. From here, instead of just going up 1 unit, we're actually going to have to go up 4 units. Okay, so 1, 2, 3, and there's your 4. Moving to the right, so if I go over 1 unit, I get to go up 1. Okay, going over 2 units, I get to go up 1/4, so that gives me that point. These are going to continue to shrink, right? You're going to end up with, well, it doesn't really matter here, but they're getting really close to the horizontal asymptote. And on this end, they also like take off really fast. What are we going to get at? -1, we're all the way up at 16. So these are going to be the only points that you get out of the graph to make. As we choose problems for you, we will, man, why would I do that? Might as well extend it out. As we choose problems for you, we'll make sure that there's a couple points that you can graph. But if you get to a situation like this where the next one just jumps, that's reasonable. Okay, anytime you multiply by a number in the front, it's going to stretch it out. And, you know, we can't have you just stretching by a factor of 2 every single time. So that one took off fairly quick. But on the flip side is that when you do stretch, that now allows those values that used to be fractions and we didn't pay too much attention to them, they actually become more of the critical numbers in these things. Domain, no surprise. The range, we're bounded at 0 and we are going up to infinity. For example 3, we're going to finally do something different than graphing. We're going to write an equation in that form. Notice that there's no h in there. I think once we start adding in too many different components and transformations, it becomes really hard to organize how you want to do this. So notice that the h is out of this here. Okay, here are the clues that we get. It's going to have that range. It's also going to contain these 2 coordinates. Now the place that we really should start, not just because it was written first, but is that range right there. Because if you go back in any of the examples and you start looking at what the ranges were, whatever that number was, whether it was on the front or the back in there, that number was the constant that you would have at the end. See, this one was a 0 because there wasn't anything that was there. What else we get? The -5 is just the constant that's there. So, in other words, what we've literally done for you here is we've given you the k value. So we know this much. F of x is going to be equal to a, we don't know a, we don't know b raised to the x power minus 1. There's one additional thing that the range tells us, and it has to do with the way that it's written. Not the number, but the way that it's written. So I'm going to give you a few seconds and see if you can think of what that tells us. Okay, what it tells us, because of the order of that, it tells us that this is a graph. This is a graph that is going to go up, or it's going to be on the top side, I should say. Now, if it's a growth function, it's going to look like that. If it's a decay function, it's going to look like that. But what we're guaranteed is that it does not exist underneath that line. Okay, so then where does that move us into our equation? It tells us that our a value is going to be a positive number. Okay, next, you get a couple of coordinates that it goes through. That is going to be your next important piece here, because that's also like what we keep seeing in the tables of that important number. Because anytime you raise, you plug in a 0 for the x, anytime you raise something to the 0 power, it becomes 1. So I'm going to plug that in. Actually, and I'm going to even set it equal to 3 because I know the outcome from putting that in. So we got a, which we don't know, b, which we don't know, but we're going to raise it to the 0 power. We're going to subtract 1, and it all has to turn out to be 3. But see, b to the 0 power is 1, so when you multiply 1 by a, you just end up with a. So very quickly, that coordinate helps us out, and it shrinks this thing down just to that. So if we add 1 to the other side, the a value is 4. That now gives us this much of a template. And notice that the a value is positive, so it matches up to what we're realizing from our range part there. So all we have left to do is to figure out what the b value is, and then that's where this last coordinate is going to come in. You can put the 8 as the output. The b we don't know, but we're going to raise it to the second power and subtract 1. So now solving, what we're going to do is we're going to add the 1. We're going to add the 1 onto the 8, which is going to give you a 9. And then you're going to have to divide by 4. Now does 9 divide by 4? No, not really. It doesn't. But let's see what happens. So we don't divide it. Leave it as a fraction. I even kind of mentioned that previously. Decimals, we might not use much of those here. But we get this. We get that 9 over 4 is equal b to the negative 2. So let's think about this if it just said 2. If it didn't have the negative and just said 2, that meant that our b value is being squared and becoming that. So what we would want to do is square root this number. We want to square root, and you can distribute that to the top and the bottom. So the fraction really isn't that bad since 9 and 4 are both perfect squares. That's going to shrink down to 3/2. But that only covers us for the 2. We still have this negative 2 that's involved. So what that's going to do is flip the whole thing over. Your b value is actually 2/3. And it might make a little bit more sense if you think about taking that 2/3 and raising it to the negative 2 power, thinking as if you're going like forwards in the problem. That's going to flip it over, and then the 2 is going to squared, and you get to your 9/4. So that part's it's a little bit of mental math, and there is a way to algebraically show how you're undoing it, but I think it's important to understand the concept of what the negatives mean and so on. In conclusion, f of x is equal to 4 times 2/3 to the x power minus 1. That's your function.